Okay, so our next goal is to do some fundamental group computations. So in this, and specifically compute fundamental groups of spheres, which we'll start today. So a definition. So a path connected space X is called simply connected if its fundamental group is trivial for every point P in X. And so today we'll see some examples. So the first one, we'll see that some spheres are examples of this. But before we do that, so lemma, the fundamental group of Rn based at 0, say, is trivial. Okay, so Rn is path connected, and so then since its fundamental group is trivial, we'll see that it doesn't matter that we're choosing the base point 0. So Rn is simply connected. Right, so proof. We've basically seen this proof before. The short answer is straight line homotopy. So what we want to do is we want to show every loop f in Rn based at 0 is null homotopic. Homotopic to a constant, that is. Right, and well, here's the proof. Define a homotopy like this. Okay, this is the homotopy. At time 0, this is doing f, and at time 1, this is just the constant map 0. And the same argument works for any other base point. So here one could say that this homotopy, we're interpolating between the constant map at 0 and f. And well, if you pick some other point instead of 0, you just put that point here. Okay. Right, so I want to point out something that we'll prove later about base points. So this condition of being simply connected, to check it, you have to check that you sort of have to do infinitely many computations. You have to compute the fundamental group at every point in X. But in fact, if X is path connected, then the answer doesn't depend on the particular point you choose. And that's the lemma that I want to state here. Oops, sorry, I'm getting my pages mixed up. So, okay, so lemma. So we'll prove this later, that if X is path connected, then the fundamental group of X based at P is isomorphic to the fundamental group of X based at Q for every pair of points P and Q and X. So let me just draw a picture to explain how or why you should believe this. So first a remark. So consequently, we often write pi1 of x instead of pi1 of x based at p. So sometimes we'll drop the base point from the notation, even though it's important for the definition of the fundamental group. These are loops based at some point. But since the point doesn't determine the isomorphism type, it's not totally unreasonable to use this notation. Right, so I wanted to just mention quickly how to think about this isomorphism. So here's a picture. We have 2 points, P and Q. And well, you can consider loops based at P, and say F is a loop based at P. And well, the content of the lemma is that loops based at P are the same as loops based at Q. So somehow we want to map, to prove this, one wants a homomorphism from the fundamental group based at P to the fundamental group based at Q. This should be a group homomorphism. That's an isomorphism. That's what one wants. And to get such a thing, well, here's how we can get such a thing. Let's choose a path, call it gamma. There's a path from P to Q, which exists because X is path connected. And we'll define this map phi by sending the homotopy class of a loop F based at P to the homotopy class. So here's a loop that you can get that's based at Q. First you do the path gamma, and then you do F, and then you go backwards along gamma. So that starts at Q, you go to P, you do the loop F, and then you go back. So that's a loop based at Q. And okay, so this is how you go from loops based at one point to loops based at some other points. As long as the space is path connected, you can do this. So, okay, so as I said, later. So later we'll show phi is an isomorphism of groups. Okay. All right. Right. So thus, to show a space X is simply connected, it suffices to prove pi1 of xp is trivial for some point P. Rather than every P. Okay, so now this brings us to the next theorem. So let's fix n at least 2. So then the fundamental group of the n-dimensional sphere is trivial. Okay, so I guess I'm now using this convention of ignoring the base point. Okay, so let me start with a little bit of informal discussion before we get to the proof. So here's one way you could try to prove this theorem. So first, so we already know that Rn is simply connected, and the n-dimensional sphere is basically Rn with an extra point via stereographic projection. Yeah, so actually maybe I will focus on S2. The proof is exactly the same in higher dimension. So for concreteness, let's focus on the two-sphere. So via stereographic projection, S2 is R2 with a single extra point. Okay, so I've drawn this picture a few times now. So we have this point at infinity, and here's R2. Right. So S2 minus the point at infinity is homeomorphic to R2. We add this extra point and we get the sphere. So we'd like to show, right, so to prove the theorem, we want to show that every loop into S2 based at some base point P, which I'm going to draw down here, is null homotopic. So there's an easy case. So observation, if the image of this loop well, let me say it this way. If the point infinity is not in the image of the loop, then the image of the loop is contained in R2, and we can use the fact that loops in R2 are null homotopic. So basically reducing to the previous argument. And you might think, well, okay, that's fine. I mean, and more generally, if the map misses any point, then you can play the same game. I mean, up to rotation, you can assume that point that's not in the image is the point at infinity, and then use this type of argument. But unfortunately, so you might think, okay, then we're done. I mean, every map of the interval, its image, I mean, this is a one-dimensional thing. We're mapping into a two-dimensional thing. Its image can't be everything. So there must be some point not in the image. But unfortunately, this is not true. So the problem is that there exist continuous surjective surjections from a closed interval to the two-sphere. And this same is true if we replace the two-sphere with the n-dimensional sphere for any n. Okay, so at first sight, this is a really surprising fact. It's a bit counterintuitive that you could find a continuous surjection. And so the name of this type of thing is a space-filling curve. And like I said, it kind of defies intuition because, well, any drawing you make, I mean, the image of a, the unit interval is compact. So like anything you draw, at some point you're going to stop and you're not going to cover everything. So this picture here is not space filling. But okay, so let me explain how you get such a thing. So let me focus on the following claim. that there exists a surjection, continuous surjection from the unit interval to the unit square. So the idea is to define f as a limit of a sequence of maps Fn. Okay, so this is, I'll put this in quotes and I'll say a little more in a second, but now let me tell you what these maps Fn are. Well, okay, so let me just draw the first few. So we're going to split up the unit square into smaller, we're going to subdivide it. So the first F1, I'm just drawing its image. So here's F1. And to get F2, we just kind of want to iterate this process. So we've split up into quadrants, and I'm going to split each of those quadrants into quadrants. And in each of those quadrants, I'm going to put the picture of F1. But I'm going to do this in a way so that the curve starts here and ends here and visits every square. So it's going to, so inside of here we have the image of F1. Here's another image of F1, another image of F1, and then another image of F1. And we connect these up to get a single path. Okay, so this is F2. And then we just keep going. So let me draw F3. This will be the last step that I draw. So first, okay, so we split it up. Then we split each of these up. And then we split each of these up. And so in each of these, we're going to draw this whole picture. And again, there's some rotation involved in this process. So the first one is like this. So that's this one. And then we do the same here. So we want it to start here and end here. So it's going to look exactly like this. So like this. It would be helpful if I had the full squares in here to draw it nicely, but okay. I'm not drawing the full squares for the sake of your time. So, okay, so now we do, I want it to end here. So I rotate it, draw it like this. We get this rather pretty looking curve. Okay, you're supposed to join all of these together. So it's just one single thing. Oh, wait, how did this get here? Okay. Okay, so this is F3, and then you just keep going. And so now I need to say something about convergence. The claim is that these converge to a map, which has the desired properties. So let me just say by analysis. So specifically, there's a theorem called the Arzela-Ascoli theorem. I won't tell you what it says, but these FNs, it tells you that these FNs converge in the space of continuous functions between these two spaces. Continuous maps. Here, topologized with the metric, as we mentioned before. So the distance between two continuous maps is the sup of the distance in R2 of the image of a pair of. So these are two paths. So we just look at how far the 2 points on the two paths are at any given time, and you take the sup over all times. I guess I'm viewing the unit cube as inside of R2, or I guess I could just put the distance in 0, 1 squared. Okay. Right. So this is okay. So convergence in this space, so they converge to some continuous function like this. And the claim is that this F is surjective. Okay, so I just realized that now I have a claim within a claim. So let me finish this argument. So the reason is, well, first of all, the image of F is dense, which follows from the convergence. Since these FNs fill out more and more of the disk. If you just take any point on the disk or on the unit square, eventually and you fix some small epsilon, eventually there will be one of these FNs that passes within epsilon of that point. And as a consequence of this, the function that these things converge to is going to have a dense image. So it's dense in 0, 1 squared. And the image is also compact because 0, 1 is the closed interval is compact. Hence closed. But these together imply that the image is everything. A closed set that's dense has to be everything. Okay, so this is, well, I haven't really proved anything, but this is the how one can justify this claim, how one can obtain these space filling curves using a little bit of analysis. Okay, so coming back to the thread, we're trying to show that we want to show something like every loop in the two-sphere can be homotoped to a constant. We know that if we can miss some point, like the point at infinity, then we're good to go. But unfortunately, it's not true that every map from the closed interval to S2 misses some point. There are surjective maps. But we will show that up to homotopy, you can homotope so that any loop misses a point. Okay, so now let's start the proof of the theorem. So we're proving that pi1 of S2 is trivial. Right, so the strategy is to show that any loop F can be homotoped to a map that's not surjective. Okay, so let's do this in several steps. So the first step is to show that the following statement. So we can decompose the closed interval into a union of subintervals that meet just along their endpoints, with the property that the image of each of these subintervals is contained in some hemisphere. Okay, so the claim is that we can subdivide into some intervals here. So here's like A1, B1, and then there's another one. These intervals meet only at their endpoints, A2, B2, and so on. So that if we look at the image of this interval under this map under F, then, well, okay, so this, whatever happens on this first little interval, it's contained in some hemisphere. So here's some hemisphere. Containing the image of this. Yeah, so this is F of A1 to B1. Okay. Okay, so this is the claim. So now let me prove the claim. So proof. Let me just start the proof in this way. So indeed, for every t in 0, 1, there exists some, well, okay, so we can choose open hemisphere. So that means not including the equator, containing hemisphere H sub t, containing F of t. So then by continuity, there exists some open interval, A sub t, B sub t. Sorry, 1 second. Let me close. This is acting slow. Okay, sorry. An open interval containing t, so that the image of this is contained in, actually, let me make it a closed interval. The image of AT, BT is contained in HT. Okay, so continuity gives us this quite easily. And now, so then, this gives us an open cover. Maybe I should say, since I took these to be closed intervals, I should shrink them. So this is an open cover. and the interval is compact. So there's a finite subcover. And this finite subcover gives us exactly what we want. So, I mean, the picture you should have in mind is like this. Here's the interval 0, 1, and we've covered it by finitely many open sets. So maybe something like this. I have one here, and then another one here, and then maybe one more. And well, at the end of the day, all we want is a decomposition into intervals that meet along their endpoints so that each is mapped into a hemisphere. So if we just break this up by like choosing some point in the intersection, this does what we want. So any point in this interval is contained. So this red, so this interval I'm highlighting here up to this this first point is contained in the red interval, so the whole image is contained in a hemisphere. And then similarly, this one is contained in the green interval, its whole image is contained in a hemisphere, and so on. Okay, so this is the first step. Okay, so we've shown we can decompose like this so that the image of each of these subintervals is contained in a hemisphere. All right, so now step 2. Now we're going to homotope f restricted to each of these intervals. So the image is a great circle arc. Which is to say, i.e., it's S2 intersect with some plane R2. This is a plane through the origin. In R3. Right, so the setup we have by construction so far, f restricted to A1, AI, BI is contained in some hemisphere H. So, okay, here's H. And here's the image of f restricted to this interval. It's contained in here. Who knows what happens? Maybe it's some space filling thing. Here's f of AI, and here's f of BI, the endpoint. And we just want to replace all of this garbage with just a straight line segment in the a great circle arc. And well, the way we can do that is with a straight line homotopy. So let's write H. Right, so observe that H is topologically equivalent to the disk. Right, I mean, if we just kind of flatten this picture, we get the disk in R2. And in this disk, right, so let's just flatten the picture and just redraw it. So we have f of AI, and then we have some mess, and then we have f of BI. And let me call the straight line segment between these gamma. So the homotopy that we want is at time, let's see, I've used t as the time coordinate here. So let me use s as the homotopy coordinate. So f sub s of t, this is a straight line homotopy, so it's 1 minus s times f of t. plus S times gamma of t. So when S is equal to 0, we're doing F. This term vanishes. When S is equal to 1, we're doing gamma. And another key point is that for every S at time AI, so this is for t in, we're only doing this on the interval AI to BI. And at AI, we get 1 minus S times, so F of AI, plus S times gamma of AI, which is F of AI. Because gamma and starts where F starts and ends where F ends. And okay, well then this is equal to F of AI. So this is crucial because this homotopy, it's fixed at the endpoints. And so this is going to allow us to glue the homotopies on these individual intervals that meet along their endpoints. So under this homotopy, these points are not moving, and that's sort of important. Okay. So this is step 2. So let me just remark, so important. The endpoints, the image of AI and BI don't change under the homotopy. So this homotopy is well defined. We do this on the individual intervals, and then we together it makes sense. All right, so now the last step, step 3, is to conclude. So after this homotopy, the image of F, so I'm still calling it F, but this is a new F, we've homotoped it, is a union of finitely many great circle arcs. So let me draw a picture. So we have some points that are connected by great circle arcs. So like this, and then like that, and like this, and then maybe it goes around the back. Okay, that's not a great circle arc, but you get the picture. Oh, and it's supposed to come back to where we started. So okay, then maybe, okay, this also doesn't look like a, okay, fine. But okay, so this implies F is not surjective. Which I'm going to leave to you as an exercise, that the union of finitely many great circle arcs has no chance of covering the 2-sphere. So that will be on, I think I'm going to put that on a homework assignment. So then we can homotope F to a constant in R2 as discussed above. Okay, good. So now let me, so I basically want to finish now. Let me make one more remark about this argument. In the case n is equal to 1. So here in this, so the same argument works in higher dimensions. Let me go back to the theorem statement. So this is for n at least 2. And this, you should go back and think about this argument. Everything I did works in higher dimensions, exactly the same. But it doesn't work for n equals 1. And let's think about why. So yeah, so I think I can fit this here. Let me make sure. So remark for n is 1, which is to say pi 1 of the circle, or yeah, I mean, i.e. S1, the argument shows any loop can be homotoped to a, well, a union of linear arcs. So you can make this map piecewise linear. So the picture is now you have the circle and up to homotopy. Okay, so the map does like some arc, and then maybe it does some other arc, and then maybe it does some other little arc that maybe goes back another direction, and then it does some other bit of arc, and then maybe it comes back around. So there's finitely many little piecewise arcs that are sort of traversed monotonically around the circle, and at finitely many points you might reverse direction, but you can write any loop like this. But this map might be surjective. So here, F could be surjective, even after this homotopy. Well, let me say it this way. So we can't conclude that F is not surjective. And so next time, we'll start to, so the next theorem that we'll head toward is a computation of the fundamental group of the circle, and we'll prove that it's isomorphic to the integers. So this argument fails for the case n equals 1 for good reason, because the circle is not simply connected. Its fundamental group is Z. And so we'll start to discuss that next time.